Welcome back. Today's going to be an exciting video for all you viewers, especially those that have been around from the very beginning. So going back 4 to 5 years ago when this channel first started out, I created one single video for the YouTube channel, Uncle Tony's Garage. During a live session that he was carrying on, some of the questions came up as far as piston pin offset. Now, this debate, again, has gone on for 4 to 5 years. Hundreds of YouTube channels have given their opinion. Experienced racers with over 40, 50, 60 years of machine shop or performance engine building have added in their 2 cents. So today we're going to go back and actually break it down to even finer detail, because once again, we have to remember some of these practices were done during the 1960s. An individual that really started this off was Smokey Yunick, the best shop in town. We have to realize that Smokey would attempt to modify engines in any way possible, even for the smallest performance gain. When you're competitive with all of the different shops in the area, or within the racing field itself on the track, any power that you can find is going to allow you to be at the front of the pack. Now, the rule books have been created over the years a lot because of the things that Smokey had tried. Smokey would also take the factory engineering platforms, the manufacturer's direction, so on and so forth, and change or alter it to see if there was additional horsepower that he could find. Now remember, as we're going into this video, with the small block Chevy platform, which is what Smokey Yunick usually would tinker around with, he changed the rod length with this combination. So he went from the short rod to the long rod, trying to, again, find that additional power. He also would change the position of the piston pin offset. Now we have to remember everything that, all of the different details that add into additional power. So while we're going to be talking about the actual piston pin offset within this video, I want to verify anyone that's building an engine. If you're installing your cam timing gear, are you using the big wheel? Sorry. Are you using the big wheel to find the precise timing for your camshaft in relation to the crank itself? Is 1 or 2 degrees going to vary whether your cam is advanced or retarded? And is there power differences in both of those actions? Typically, by advancing the camshaft, you're going to move the power graph or the power into the lower RPM ranges, where if you retard the timing, more of your power is going to be shifted up in the RPM range. But you want to verify exactly the position of your cam in relation to the crank degrees. Is there additional power in that? Okay, depending on all the components put together in the package, you might want to take advantage of the higher RPM. So if you have higher flowing cylinder heads or higher compression, or you're in a racing application where you're sustaining higher RPM, you want the power to occur further in the power diagram. So every engineering aspect within an engine can determine where the power is going to occur. Now, does that mean it's going to make more power? If you're concentrating on a higher RPM, yes, you're going to make more horsepower. If you're concentrating, say if you're in an all-wheel drive vehicle or a heavier vehicle, you want the power to be more advantageous towards the torque multiplication that the engine can create. No different than if you're on an engine dyno. Here's another example. There's thousands of videos out there with engine dyno testing. Let's go to Horsepower TV, for example. If the gentlemen have just built an engine, it's on the dyno, and they run at 34 degrees, they might say, okay, the graph is showing a little instability, so let's add some timing to the ignition and see what that does. And it will pick up or smooth out the power curve. So is timing directly related to horsepower? Is there additional horsepower within the timing? Yes. So while this debate has gone on for 5 years now of whether or not the piston pin offset is worth power, we need to break it down to every single aspect to prove that there is power within the design. And it's magnified with the way the engines were assembled 50 years ago. So what I have drawn up here today is basically your cylinder head, your piston with the cylinder walls, your connecting rod, and I have two positions, extreme positions of the piston pin offset, whether it be a negative or a positive location within the piston. Down here, hopefully you can see it, is a modified a crank journal. Okay, so not the entire 360 degrees of the crank, just one single crank throw connected to the big end of the connecting rod. Now, we're going to go through in this video, we're going to go through the use of pressed pins compared to floating piston pins. That was the average mechanical process 50 years ago. If you haven't seen my variation in the previous video about the angularity of the connecting rod and where the weak spot normally occurs, okay, go ahead and tune into the last, I believe it was 2 videos ago. It's also going to be affecting the quench, the timing of when the quench occurs between the piston and the cylinder head in relation to the crank degrees. So not only the timing of the crank degrees, but the timing of the crank to the camshaft timing, the thrust, the angularity of the connecting rod within the crank degrees, the angle that the connecting rod is, and the thrust that it's causing the piston to move to one side of the cylinder or the other. So that's going to be a variable between V8 engines and the direction of rotation of the crank. We're also going to talk about the tilt, the actual piston cocking within the cylinder itself, creating friction at the skirt. We're going to get into the cam timing, once again, the relation between the crank and the cam timing, and the ignition timing, because by altering the position of the piston pin offset, it alters every single one of those variables. Is there power within each one of those variables? So while the engineers of Chrysler back in the day did print out that by swapping their pistons from their factory design around was advantageous towards power, we have to figure out why the engineers of the 1960s were able to formulate that process. Okay, so we're going to start out and we're going to work from the top down, starting off with the spark plug and the combustion chamber. Now, your typical small block Chrysler, big block Chrysler, which the engineers of Chrysler were talking about, this is separate from the Hemi. Okay, let's go back to 1964 with the 426 max wedge. Okay, let's use that as a basis for today's discussion. Now, the max wedge big block Chrysler obviously used a wedge style combustion chamber. And during the racing applications of the early 1960s, with their heavily modified pro stock race cars, like the Savoys and so on and so forth, that were equipped with aluminum body components to altered wheelbases, moving the rear axle closer to the front of the car. This is when the research and development was occurring with piston pin offset. Because in a wedge engine, something that has a quench area within the combustion chamber, as the piston approaches to the top dead center position, a quench area is created. The smaller that quench area is, the more the gases that are in that portion of the cylinder are forced in the direction of the spark plug. Easy enough. Now, if you were to take a 426 max wedge and soften the chambers like modern day engine builders do when they're utilizing a forced induction or a nitrous application, doming the combustion chamber, the quench has been changed. The air is still moving towards the spark plug, but not as an intense rate. With the flat portion of the cylinder head in a wedge style chamber, as the piston is approaching top dead center, the distance, the quench distance, has a much more abrupt effect on the gases within the chamber itself. Now, again, by moving piston pin location, you're altering the timing of when the piston reaches top dead center in relation to the degrees of the rotation of the crankshaft. So by altering the piston pin location, you can actually alter the timing of top dead center to the relation of the crankshaft by up to 8 degrees. If the connecting rod or piston pin location is directly in the center, the timing of the piston to reach top dead center can be advanced 4 degrees or retarded 4 degrees. So once again, depending on where in the RPM range that you want to achieve the greatest power production, whether it be at the lower torque end of the RPM range or the higher RPM horsepower range, you can actually alter the timing of the top dead center in relation to the crankshaft. Now, that will be mirrored on how you install the timing between your crank and your cam timing. So if you are advancing the piston to top dead center position by altering or advancing the pin towards the positive side of the piston, you are increasing the timing of the piston to reach top dead center 4 degrees prior than it would be if it was mounted straight up. That is going to be reflected then into the cam timing. By advancing the cam, you're going to be creating more of the lower RPM. Follow along? It's just the opposite of what the piston is doing. By causing the piston to reach top dead center 4 degrees sooner, you can subtract, you can retard the camshaft timing in order to create more torque, creating a different power band. Is it worth more power? Again, this is the debate that's going on. You have to break things down into the minuscule little changes within the engine to verify your theories. It's all connected. Any mechanical change within an engine, even a compression difference of 0.1 increase or decrease, is going to be a noticeable change within power output. Is it going to be something you can feel in the seat of your pants? No. But if you're jumping from 9-to-1 compression to 12.5-to-1 compression, you're going to be able to feel that in the seat of your pants. So when we're talking power gains or losses in piston pin offset location, the power is not going to necessarily be noticeable in the seat of your pants, especially with engines like small block Chevys that Smokey Unic was working with. When power may be achieving 1 horsepower per cubic inch, if you add 5 horsepower, are you necessarily going to be able to feel that in your seat of your pants? Probably not. But if you're finding 5 horsepower gain within piston pin location, and you find another 5 horsepower because of lightening the connecting rod, or another 5 horsepower found in additional cam timing, the combined effort of finding small little points of horsepower, in the end, the final goal, you are going to have enough power or additional horsepower to actually feel it in the seat of your pants or within the performance on the track. Okay? Now let's move down to the actual piston and the pin itself. Typically from the factory, piston pins are located to the point where they're going to be favoring the thrust side or the tilt of the piston. So they're going to be in the direction of the crankshaft rotation. Now, if you are thinking about a V8 engine, doesn't matter which bank you're talking about, the crank rotation is always in the same clockwise motion. So the thrust side of either bank of the engine is going to be towards the direction of the crankshaft rotation. If you were talking about an inline six-cylinder, say a Ford 300, the thrust side remains exactly the same. It's within the rotation of the crankshaft. Now, in a V8 application, typically the pistons were set with the piston pin offset to the exact same side of the piston. So if they are reversed, one bank is going to have the piston pin offset away from the thrust side. Okay, follow along with this. So by taking the pistons and swapping them around and altering to the banks, what are you doing? Are you reducing the thrust in the engine? You're only reducing the thrust of the piston pin offset by doing that flipping around to only 4 cylinders. Because once again, only one side of the V8 has the piston pins facing one direction. The opposite side, the piston pin is offset to the opposite direction. So by flopping them around, you're just changing the bank of the side of the piston pin offset. All right? So is there a power gain in that? Not necessarily. But once you start getting into aftermarket pistons, the piston will have a specific location of where it's supposed to be going, whether it's a driver or passenger side bank of the engine, to where you can order the pistons with an equal offset to all of the pistons, but they're going to be favoring one side of the pistons. The factory pistons used during the 1960s in the 1964, let's say Sport Fury or 426 Max Wedge, the pistons were cast exactly the same. They could be altered in the different holes of each bank. Follow along, correct me if I'm wrong. So by swapping the pistons from one bank to the other and reversing them, you're just changing the piston pin offset equally to both sides. But within testing, where piston pin offset has been the test platform that has shown the greatest performance gain, is in a single cylinder engine. So let's take your typical lawnmower engine, your Briggs & Stratton. The piston pin on those smaller one-cylinder engines is offset. So if you were to take that piston in that engine and swap it around, what would you necessarily be doing? You're going to be altering the timing of when the piston reaches top dead center in relation to the position of the crankshaft. So by offsetting the piston pin towards the positive side, which allows the piston to reach top dead center sooner, it's changing the timing of the top dead center to the relation to the timing of the crankshaft. You are causing it to reach top dead center in advance to the zero of the crankshaft rotation. You're going to be moving the power band lower in the RPM range. If you retard or move the piston pin to the negative side, you're doing just the opposite. So some of you single cylinder Briggs & Stratton alcohol junior dragster racers, go ahead, if you got an extra piston, okay, take it out, look at it. Which direction is the piston pin offset to? Is it moved to where the piston is going to reach top dead center when the crank journal and connecting rod are perfectly straight to underneath the piston? Or is it to the point where it actually allows the crankshaft to rotate approximately 4 degrees past the zero of the crank rotation when the ignition or the piston reaches top dead center. Because once again, as the piston is coming up, everything is within a line. But if you alter the position of the piston pin to the advance, the piston actually reaches top dead center before the alignment of the rod or the connecting rod and crank journal are perfectly in line, straight line, in relation to the plane of the cylinder head. It's not. The piston reaches top dead center sooner. So again, going back to the dyno sessions, if anybody is trying to find the prime ignition timing, something that goes from 32 to 35 degrees, is there a noticeable power gain with that advantage of advancing the timing from 32 to 35? Every engine will have a sweet spot of where it makes the most amount of power, has the flatter power curve within the RPM range. All of it's connected. Now, even if you find, say, small block Chevy, say that you determine 35 degrees advanced timing with the ignition is the optimum timing. If you change even one other timing aspect within the engine, whether it's the camshaft timing, advanced or retarded, or the offset of the piston pin, your 35 degree optimum ignition timing will change. By moving the piston pin location to the positive side, allowing the piston to reach top dead center sooner, approximately 4 degrees, your 35 degree optimum ignition timing is actually going to change to a 31 degree optimum ignition timing. Is there a power gain in changing the ignition timing? Yes. Is it enough that you're going to feel it in the seat of your pants? No. Are you going to see 40, 50 horsepower gains of a small block Chevy with a 4 degree ignition timing? No, but the engine is going to either run smoother or it's going to ignite the fuel more efficiently. Is it going to deter detonation from the fuel because of the timing of the ignition? All of these variables go into piston pin offset. So by the Chrysler manufacturers swapping the pistons, they're only doing that to 4 cylinders. They're only altering the piston pin offset to one bank. Can anybody guess which side of a V8 engine, if you're looking at the front of the vehicle, which side is more advantageous to swapping the pistons around? Okay, again, the rotation, it's clockwise as you guys are looking at this. The factory would set the piston pin offset to the side of the thrust. Okay, so say the rotation is this direction, clockwise. Piston pin would put in the advanced location. Now that is also opposite of the quench. But which side of the engine? Because the quench is on the inside of both banks. The spark plugs are on the outside, the quenches are on the inside. So by swapping the pistons around and the offset of the piston pin, you're putting the pin under a different location underneath the quench, but only for 4 cylinders, half of the engine. Okay? The other side, by swapping the pistons around, you're actually putting the piston pin under the opposite side, the piston or the spark plug side of the combustion chamber. So while you might be gaining some on 4 cylinders, you're actually losing on the other 4. By swapping the pistons around, you're just changing the side of the bank that's taking advantage to the offset piston pin location. But if you're building a V8 engine and you're custom ordering pistons with a all positive piston pin offset to the rotation of the crankshaft, those piston pins are going to be on the exact same side. But the cylinder heads, the quench, remains the same. Follow along with this? So is there additional horsepower necessarily with the piston pin offset? It is not necessarily achievable on a V8. But once you start getting inline engines, whether it be a straight 6, a 4-cylinder, or a single cylinder engine, the offset is moving either underneath the quench or away from it. A V8 engine, because of the altered banks of the engine and the relation to the cylinder heads in the quench area to the piston itself, it's not that much of a difference. So they were taking technology they learned with a single cylinder engine and transferring it into a V8, realizing that only half of the cylinders are going to take advantage. But the advantage that 4 get from altering the piston pin location is actually a negative to the other side. But now let's move on to the piston, the tilt, and the thrust. Once again, the thrust side remains the same in the cylinder. It's always to the rotational side of the cylinder. So if we have a clockwise rotation, it will always be the right side of the cylinder. As you were looking at the engine, that will be the thrust side. In every instance, whether it be a V8, inline, or a single cylinder engine, the thrust side is always the side that the rotation runs into. So then at that point, altering your piston pin location is going to be something that's going to alter the load, the tilt of the piston, and how the slap, as they call it from the factory, that reduces the slap noise that you might hear. Okay? Follow along? Now we also have to go back to the 1960s with my previous video talking about the difference between the pressed pin and a floating pin piston design. In the 1960s, especially in that 1964 426 Max wedge, the pistons were constructed with a pressed pin design. So no matter what the offset is of that piston pin location is, as it is achieving top dead center, once the quench starts creating pressure between the cylinder head and the piston, there is more force between the quench and the piston on the quench side of the piston. Follow along? Check my math here. It's also creating the piston to reach top dead center sooner. So it's getting into the quench area sooner within the degrees of the crankshaft rotation. The thrust side still remains to be on the opposite side, the direction of the crankshaft rotation. Now with a pressed pin, in the previous video I mentioned that when forces of the piston are starting to push down, okay, no longer the stretch of the connecting rod pulling the piston away, it is now compressing the connecting rod and piston up towards the combustion chamber. And as combustion pressures increase, the force down on the piston also pushes down on the piston pin. And as the connecting rod rotates, it is under pressure. As compression pressures increase, it is squeezing any oil that might be between the piston and the connecting rod pin to the sides, and it's now rotating underneath that pressure, and it continues to increase as it reaches top dead center and the ignition timing occurs. At that point, the cylinder pressures increase dramatically. Now, the sooner you can get the piston to top dead center, the sooner combustion chamber pressures are going to increase. And it also determines at what angle the connecting rod is into the relation of the crankshaft. So by advancing the piston pin location to allow the piston to reach top dead center 4 degrees sooner in a crankcase rotation, the crankcase is also retarded because it's going to be just the opposite. The crankcase location is going to be 4 degrees behind top dead center. Now, as ignition pressures increase from the ignition, it is now traveling again for 8 degrees, 4 degrees prior, 4 degrees after. It is continuing for 8 degrees as cylinder pressures are increasing. So by the time they reach a higher amount, because of the flame travel and the increased pressure from the ignition cycle, the crank and connecting rod angle are now retarded to the point where the gases in the combustion chamber are going to be greater once the crankshaft rotation and the piston begins to move down. All right, so it isn't all related to the actual timing of what things going on. And the piston pin location when the pressure is being met is also going to allow the piston pin to have a longer life. It's going to be able to withstand more abuse. So say that we're going back to the 426 max wedge. By altering the piston pin location to one side, okay, it's a V8 again, to one side, all the pistons are manufactured in the same orientation. You can turn them around, be exactly the same, but it alters the direction of the offset from one bank to the other. Now let's say that if you were to take a 426 max wedge and chop off just one single cylinder, so you're just working with cylinder number 1. Let's call this cylinder number 1. The thrust side remains to the right side. The timing of the piston is altered by the piston pin location. If it's advanced, it advances it approximately 4 degrees from 0, straight up and down. Or it can be retarded 4 degrees to retard the timing of top dead center to relation of the crankshaft rotation. Is there noticeable power in this design? It might be enough that it creates 5 horsepower. Okay, is that noticeable in the seat of your pants? What it's also changing is the amount of pressure being exposed to the connecting rod and piston pin. So if you can reduce the stress on the connecting rod and piston pin, what are you able to do with the engine to create more power? So it's not necessarily additional power in the exact same RPM range. It's more power because of the additional RPM you're able to achieve because there's less stress being put on the parts. So you can stretch the RPM that they're capable of handling. So by altering the piston pin location, you might be able to change your red line of your engine from say 6,500 RPM to 6,700 RPM. Is there additional horsepower in 200 additional RPM of the engine? Yes. Is it noticeable enough that you're going to feel it in the seat of your pants? It might be the difference of a thousandth of a second in a quarter mile. In circle track racing, it might be a very small variable that cannot be connected directly to the modification, but it could be the difference of racing 50 laps or going 60 laps before engine catastrophe happens. It's reducing the stress on the components. The piston pin pressed pin, where you have to actually heat the connecting rod, slide it in, that piston pin is only rotating as much as the swing of the pendulum of the connecting rod. The piston pin is only rotating approximately 50 degrees, and then it's returning going back the opposite direction. It's never turning all the way around. So the flex and pressure being placed onto that piston pin is always going to be in one arched direction. The forces into the metallurgy of the pin is only going to be shared on one side of the pin. While the top is being stretched, the bottom is being compressed. Because there's more pressure during the combustion cycle of the compression of the piston pin than there is at the bottom dead center when the piston is just being swung by the weight of the combination of the connecting rod and the piston onto the crankshaft. As it's being pulled, it's only dealing with the weight. Where when it's being compressed, there's the pressure of the combustion cycle being forced down on the pin. So there's not an equal exchange of the force on the piston pin from the combustion pressures to the bottom dead center release or pull in the opposite direction. So your pin is always going to be forcing down one direction. By having a floating piston pin, that pin is able to rotate within every pendulum swing or rotation of the connecting rod, allowing that pin to rotate to where it gets exposed to the pressures of a running engine more equally during its life expectancy. Is there more power in that? No, but it allows the engine to be taken further in the extreme examples. It will withstand more abuse. Now, in 1964, going back to the 426 Max wedge, with the pressed pin design, which was shared throughout the 1970s and even into the 1980s. With a pressed pin, as the pin was being fixed to the connecting rod, when it would turn, that change within the piston pin rotation would be transferred into the piston. It would actually cause the tilt or the cocking of the piston because of friction to favor one direction. Again, as the connecting rod is turning over, it is forcing the piston to turn clockwise, causing the skirt of the piston to make contact with the cylinder wall here. This side of the piston, this bottom of the skirt is making contact with the cylinder wall on the intake, or excuse me, yes, on the compression stroke. The thrust side never changes because it always stays in the rotation of the crankshaft. Now, as a pressed piston pin construction forces the piston to turn by going into a floating pin, it reduces the amount of friction caused between the piston skirt and the cylinder wall on this side of the piston. The thrust side remains this side of the piston. Now, allowing that piston to tilt or cock within the position of the cylinder, it lifts this skirt side of the piston away from the cylinder wall on the downward motion. So it's literally creating a ski. Any kind of water skiers or downhill skiers, it is actually causing the tilt to allow the oil that is on the cylinder wall to go out further on the piston before it's being squeezed in between the piston and the cylinder wall to lubricate it. So any one of you can pull out a piston of any used engine you ever had, look at the sides of the skirts. The thrust side of the piston normally has more wear and tear within the marks on the piston compared to the inboard side of the opposite direction of the crankshaft rotation of the skirt. But you'll notice the wear and tear, the markings on the piston on the inboard side is going to be on the bottom of the skirt. But if you look at the pistons, the thrust side of the piston, the wear and tear is not at the very bottom of the skirt. It's not down here. It's up more towards just underneath the oil control rings. So if the offset piston pin location was only to address the thrust of the piston, all of the wear would be even from top to bottom of the thrust side of the skirt of the pistons. But it isn't. Look at all of your engines. They're opposite. So piston pin location helps balance. It's literally the teeter-totter of the piston as it is rocking in the cylinder, depending on where the pressure is, both from the thrust of the rotation of the crankshaft and the amount of pressure being exposed to the top of the piston. Going up a little bit more, again, going back to the quench. When a piston is approaching top dead center, the quench side is causing the piston to cock in the opposite direction of thrust. As the ignition happens, the piston will come back in the teeter-totter and plateau. It is then forced in the direction to where this is going on, to where the piston is cocking towards the thrust side because of the piston pin rotation. With a floating pin, that pin is introducing less friction in the direction to cause the piston to tilt. So more modern day engines, even though the thrust side has remained the same, Let's talk about an early 1990s Magnum engine utilizing a floating piston pin. The thrust side remains the exact same as the 426 Max wedge, right? But you'll notice the pistons have a different wear pattern on the skirts. It will be more even from the center to the bottom of the skirt on the thrust side. You'll have a much smaller area of destruction, if you want to call it, or wear and tear on the piston, to where it only covers just the bottom inch of the skirt on the inboard side. That is how much reduction in friction, the change of going from a pressed pin to a floating pin. Now, is the 1992 Dodge Magnum, does it have the exact same piston pin offset, say that to a 1968 360? They're identical. What's the difference in the piston design? They've gone from a pressed pin to a floating pin. Is there additional horsepower in that? Or is it the durability or longevity of the wear and tear between the components and the reduced friction from a 1968 to a 1992 small block Chrysler? Now, another thing going back to Smokey Yunick. Remember back in the late 1960s when, or even 1970, when Smokey Yunick was testing the different connecting rod lengths. From the 5.56 to the 5.7 to the 6-inch connecting rod in a small block Chevy. What the cranks, okay, let's use the 350. With the 350, all of those connecting rod lengths could be utilized. It alters the location of the piston pin within the piston itself. Okay? Throughout that testing, what did Smokey Yunick actually prove? Was there more horsepower gain from a longer connecting rod? Or did this shorter connecting rod create more power? And where in the RPM range did it change? Because now by changing the connecting rod length, you're mechanically changing the piston speed, the rod to stroke ratio. With a shorter rod, you are speeding up the piston as it's moving up and down because of the much more aggressive connecting rod angle in relation to the crankshaft rotation. A longer rod does not necessarily create more horsepower. A longer rod reduces the speed of the piston going up and down compared to the 5.56. Okay? So Smokey Yunick, if you go back and they're actually detailed within his articles and within his preaching, in 1968 he used the short rod. He went to the 5.56 and his engines were revving at 8,000 RPM. In 1968, he would blow engines up. In 1969, he went to the longer rod, the 5.7. He didn't have as many engines blow up. He was also able to achieve a little bit higher RPM, approximately 200 RPM more before he met his red line. In 1970, his white Camaro, his 1969 Camaro with the the boxy hood scoop, so on and so forth, with the Muncie 4-speed, and shift gate transmission, he's able to achieve the fastest times he ever did. And in those combinations in 1970, in the small block Chevy, Smokey was using a 6-inch connecting rod. Now, depending on the length of the connecting rod and the piston pin location, what does it alter? A shorter rod will multiply the piston pin offset within the timing to the crankshaft rotation in a greater amount than it does with a 6-inch connecting rod. With the shorter connecting rod, instead of these offsets creating a 4-degree difference in piston to top dead center timing compared to crankshaft rotation, it would actually alter it 8 degrees. So between advanced and retarding of the piston pin location, There's actually a 16 degree crankshaft rotation difference of when the piston reaches top dead center from 0 straight up. So by advancing and offsetting the piston pin towards the positive side, it was 8 degrees. It was reaching top dead center 8 degrees sooner with a short rod and only 4 degrees advanced with the 6-inch rod. In relation to the crankshaft rotation. So yes, is there additional horsepower that can be measured on a dyno on that? Okay. Also, between 1968 and 1970, Smokey Yunick almost took off a full second from his pro stock racing times, going from a short rod spinning 8,000 RPM to a 6-inch rod in 1970 spinning 8,500 RPM. Is there more power from 8,000 RPM to 8,500 RPM? Yes. If you're turning the exact same RPM and you're doing nothing but swapping pistons in a Chrysler, are you going to necessarily be seeing something that makes less than a horsepower per cubic inch? Are you going to necessarily be seeing any kind of performance gain on a dyno? No. But when you're talking the difference between 8,000 and 8,500 RPM, there's additional power available within the timing of the reaching top dead center into the crankshaft rotation. Now, Smokey Yunick's 1970 350, was he making 1 horsepower per cubic inch? During the era when every manufacturer was trying to attempt 1 horsepower per cubic inch, in what year and with what engine was 1 horsepower achieved? 1967, 1968, 1969, 1970. Out of the small block Chevy camp. What's the difference in those years to allow those engines to achieve 1 horsepower per cubic inch? Because both between the 327 and the 350, the Corvette or Camaro engines, they were able to achieve more than 1 horsepower per cubic inch. Would you take a guess at which direction the piston pin is on every single piston in a small block Chevy of that era? Can you swap the pistons around in the small block Chevy from 1969? Let's say a 1969 Z28 302. Another Smokey Yunick alternative. All the pistons have the piston pin offset in the same direction, in the thrust side of the engine. The 4 cylinders of either bank cannot be swapped around. They are directional pistons. Is there more power? Yes. When the total outcome is planned to take advantage of every mechanical component in relation to the timing of the crankshaft rotation, the timing of reaching top dead center, the timing of when the quench is being introduced into the combustion process, in relation to the timing of the ignition, and to the speed of the piston going up and down, reduced with a longer connecting rod. A longer connecting rod also improves the angularity of the connecting rod to the center of the crankshaft. Is there additional power in that? Yes. So while you had individuals from Hot Rod Magazine and Engine Masters Challenge try to test out a small block Chrysler of, yeah, we did the swap, and they didn't show it. They just said, oh, we didn't see any noticeable power gain. No, you didn't, because the mechanics have stayed the exact same. But when you start getting the aftermarket or with engines where the piston pin offset is designed into the piston design for either retarding or advancing the timing of top dead center in relation to the crankshaft, there is additional power. Now, David Vizard had also admitted that he had tested something during the late 1980s on a small block Chevy where he noticed, I believe it was a 15 horsepower, or maybe it was 30, I believe a 15 horsepower difference within a combination. Okay. Was it entirely because of the piston pin offset, or is it because the connecting rods that he used were longer? Is it a direct apples to apples comparison? But the mechanics verify, the engineering schematics verify the advantages to having an offset piston pin because of the timing into the relation to the rotation of the crankshaft. So let's review. We talked about the difference in construction and assembly of pistons from the 1960s to modern day engines, going from a pressed pin to a floating pin. We've talked about the timing and the quench side of the combustion chamber. On a V8 engine, they're opposite. On an inline engine, they stay on the same side. So the advantage is going to be more noticeable on a inline engine than it is on a V8. The timing is also going to change of when it reaches top dead center, depending on the piston pin location and connecting rod length. It's going to change the abuse that the piston rocks or cocks within the cylinder because of the piston pin location and the teeter-totter effect of the piston. It's going to alter camshaft timing. Okay, you're going to see that maybe you're going to get an advantage by advancing your camshaft when the piston is reaching top dead center sooner. It's also going to alter the prime ignition timing of when the engine achieves its greatest power potential. Well, that's 32 degrees to 35 degrees ignition timing. And it comes even more important with more modern day engines. Now, I forgot one other aspect, and that's with higher compression pistons. The quench of a piston changes when a dome is introduced into the piston design. The quench is interfered with. With a dome piston, the quench area of the combustion chamber is now shared over a greater portion of the piston because the dome is encroaching on the casting of the cylinder head at an equal amount. So instead of having a quench pad on just one side of the piston, it is now shared equally across the top of the piston. The actual design of the dome matches the combustion chamber. So the entire surface of the piston mirrors the impression of the combustion chamber inside the cylinder head. The entire top of the piston becomes a quench. When you are using a dome piston, you are not taking in the aspects of addressing which side the quench area is on. And in a domed piston design, you cannot take the pistons, turn them around and swap them to the other sides because they put the dome underneath the quench pads. Easy enough. With modern day engines, okay, things that use mechanical or centrifugal force camshaft advanced mechanisms. The mechanical cam advancement mechanisms, not the electronically controlled variations that are being used today. Now, the mechanical designs within dual overhead cam engines. The initial design into those mechanical advance or retard systems is matched to the crankshaft rotation. It is also incorporated to the timing of when the piston reaches top dead center. Because again, the piston pin offset is going to change the timing of top dead center in relation to the crankshaft rotation and to the camshaft timing. There's 3 different variables connected to the piston pin offset, all having to do with the timing. Is there additional horsepower with an addition or advanced timing? Yes. So while some apple-to-apple comparisons on a dyno are not going to show necessarily an advantage by having a altered or swapped around piston pin offset, the higher the performance ability of the engine, the greater the greater the performance gain is going to come from an offset piston pin. The Chrysler engineers that documented having to take the pistons out and swap them around were taken from the racing days and experiences they had with the 1964 426 Max Wedge. It worked with the Pro Stock engines of 1964. They put it into the documentation of the Chrysler handbooks, and it crosses over to every single Chrysler platform or V engine of the similar design. So the small block Chevy, the small block Ford, the big block Chrysler, anything of the wedge design is going to take advantage from having that offset piston pin in the direction of what they found out to be true in 1964 in the 426 Max Wedge. Does that information stay true today in every modern day engine? You will not find one single high performance modern day engine that does not have a piston pin offset towards the positive side of the piston. It's not about the thrust of the piston and balancing it out. It's about the timing of the piston reaching top dead center to the relation of the crankshaft rotation and the cam and ignition timing. So with that, yes, almost an hour. But within 1 hour, you have learned more information that has been shared within the last 5 years, even going back to the very first video I created 5 years ago for the channel Uncle Tony's Garage. For 5 years, so-called professionals in the performance industry have been coming out and saying there's a debate going on. There is no debate. It is the lack of intelligence and knowledge of how the mechanical components work together. The engineers in 1964 with the 426 Max Wedge were more intelligent than any of the individuals on YouTube today telling you that an offset piston pin is not worthy of addressing. It's that simple, folks. No matter how many degrees you might have as a mechanical engineer or as a rocket scientist, the engineers in 1964 did not have the equipment to test things in a laboratory. Their proving grounds were on the racetrack when the 1964 426 Max Wedge was wiping the floor over every other manufacturer. Have a good one.